Hello everyone and welcome to Looking for Pythagoras 4.3. Again, our learning target is I will understand how to convert a rational number fraction to a decimal and back. Yesterday, we converted a rational number from a fraction to a decimal. Today, we're going to look at converting a decimal back to a fraction. Our aces for 4.3 are 11 through 18, 32 through 34, and number 38. So we're going to be today, as it says here, representing decimals as fractions. Now, please take good notes today because we're going to get into some of it's going to be fairly straightforward, but some of it can get a little confusing. So please, please, please take really good notes and pause the video if you need to, play it back, use your resources, but don't just watch it through and hope that you remember everything. Please take good notes, okay? So it tells us in problem 4.2 you found that you can represent every rational number in fraction form as a terminating or repeating decimal. So rational numbers, they can be um, written as terminating or repeating decimals. In this problem, we're going to investigate how to do the reverse and represent decimals as fractions. And it asks us, can you represent every repeating or terminating decimal as a fraction? So that's something I want you to take a moment, pause the video, think about that based on what you know from converting a fraction to a decimal. What does this information give you to tell you whether it can be converted from a decimal to a fraction? Okay, looking at the problem, on a copy of the table below, write each fraction as a decimal. So we're going to go through 1 divided by 9, 2 divided by 9, so on and so forth, 1 divided by 11, 2 divided by 11. Fill all of this out, and most importantly, describe any patterns you see in your table, okay? Again, and this gets started on page 67. Use the patterns you found in question A. Question A is the one right back here, okay? This table, use this table to write a decimal representation for each number. Notice these first two have 9 for denominators, these two have 11 for denominators. Use the patterns you found in part A to be able to come up with decimals for that. Then use that knowledge you have and see if you can find a fraction equivalent for each decimal, if possible. So we had some patterns in A and B. See if you can apply those to this, and if they're all rational or not. We might have an irrational one or two that might make it kind of hard. Then we get into part D, and this is where you're really going to want to take some good notes. It says the patterns from question A can help you represent some repeating decimals as fractions. What about other repeating decimals such as 0.121212? Well, we need a method that will help us find an equivalent fraction for any repeating decimal. And it tells us here that we can set x equal to 0.12 repeating. And then what is 100x? Is it still a repeating decimal? Well, if we take x times 100, that means we're going to move our decimal place 2 spots, because if we took it times 10, we'd have 1.212. And if we take it times 100, we get 12.1212, which is what we have right here. It says, is it still a repeating decimal? Well, yes, we still have our repeating decimal happening here. Then what we want to do is subtract out our original x from our 100x. So we have 100x equals 12.12 repeating, and we have x equals 0.12 repeating, and we're going to subtract this x from the 100x. So we set it up like this, and with our equals sign underneath, and 100x minus x gives us 99x. Well, what's 12.12 repeating minus 0.12 repeating? That's what we're looking for here. And it says, is the answer for 99x still a repeating decimal? Find a fraction form by solving for x. And why do you think this method starts out by multiplying by 100? I kind of explained that to you. And then it wants you to use this method to write each repeating decimal as a fraction. Now, I'm going to have you watch a little video here that's going to explain this a little further. So hang with me. Take good notes on this too.
In this video, I want to talk about how we can convert repeating decimals into fractions. So let's give ourselves a repeating decimal. So let's say I had the repeating decimal 0.7, and sometimes it'll be written like that, which just means that the 7 keeps on repeating. So this is the same thing as 0.7777, and I could just keep going on and on and on forever with those 7s. So the trick to converting these things into fractions is to essentially set this equal to a variable, and we'll just do it step by step. So let me set this equal to a variable. Let me call this x. So x is equal to 0.7, and then the 7 repeats on and on forever. Now what would 10x be? Well, let's think about this. 10x. 10x would just be 10 times this. So it would be, and we could even think of it right over here. It would be, if we multiplied this times 10, you'd be moving the decimal 1 over to the right. It would be 7.777, on and on and on and on forever. Or you could say it is 7.7 repeating. Now this is the trick here. So let me make these equal to each other. So we know what x is. X is this 0.777 repeating forever. 10x is this, and this is another repeating thing. Now the way that we can get rid of the repeating decimals is if we subtract x from 10x, right? Because x has all these 0.7777. If you subtract that from 7.77777, then you're just going to be left with 7. So let's do that. So let me rewrite it here just so it's a little bit neater. 10x is equal to 7.7 repeating, which is equal to 7.777, on and on forever. And we established earlier that x is equal to 0.7 repeating, which is equal to 0.777, on and on and on forever. Now what happens if you subtract x from 10x? So we're going to subtract the yellow from the green. Well, 10 of something minus 1 of something is just going to be 9 of that something. And then that's going to be equal to, what's 7.77777 repeating minus 0.77777, what, going on and forever repeating? Well, it's just going to be 7. These parts are going to cancel out. You're just left with 7. Or you could say these two parts cancel out. You are just left with 7. And so you get 9x is equal to 7. To solve for x, you just divide both sides by 9. Let's divide both sides by 9. Well, I could do all 3 sides, although these are really saying the same thing. And you get x is equal to 7/9. Let's do another one. I'll leave this one here so you can refer to it. So let's say I have the number 1.2 repeating. So this is the same thing as 1.2222, on and on and on. Whatever the bar is on top of, that's the part that repeats on and on forever. So just like we did over here, let's set this equal to x. And then let's say 10x, let's multiply this by 10. So 10x is equal to, it would be 12.2 repeating, which is the same thing as 12.222, on and on and on and on. And then we can subtract x from 10x. And you don't have to rewrite it, but I'll rewrite it here just so we don't get confused. So we have x is equal to 1.2 repeating. And so if we subtract x from 10x, what do we get? On the left-hand side, we get 10x minus x is 9x. And this is going to be equal to, well, the 2 repeating parts cancel out. This cancels with that. If 2 repeating minus 2 repeating, that's just a bunch of zeros. So it's 12 minus 1 is 11. And you have 9x is equal to 11. Divide both sides by 9. You get x is equal to 11 over 9.
So hopefully that's helpful, and then we'll help you to get the answer here and determine whether it's still a repeating decimal. And then continue that on for these repeating decimals to get some practice with that. That's the 5 down on the bottom here is the same as what I have up here. It's just that here we would have room to work on it in the classroom if we need to. Then part E, tell whether each statement is true or false. You can write any fraction as a terminating or repeating decimal, and you can write any terminating or repeating decimal as a fraction. So answer whether those are true or false. Again, our ACEs, 11 through 18, 32 through 34, and 38. Hopefully this was very helpful for you, and let me know if you have any questions when you get to the classroom.